So here's a video on how to kind of finish up your presentation. I made a sample presentation for you, and all the links and everything will be in at the end of the lab manual. So that's a link for the template, and here's a link for the Google Drive to where to store your data, and ultimately here's a video that you will be watching right now. So let's just walk it through, and feel free to apply templates, but the title, your group member names, and your TA name, right, and your group name too. And you can give yourself a different name, but then just put 1, 2, 3, whatever in there as well. And so then a slide on stochastic resonance, in your own words describe it, and then find an application that is of interest to you or the group, just one, right, and then put that reference along with that reference. Then you have to have your Schmidt trigger, and this is just for one person's, right. This is a Schmidt trigger, this is what you measured, and the VH was what, right? It's supposed to be either 0.6 or 0.4 volts, but it'll probably be a little bit different for each of you. And so it's just a sample, right? And here you can also explain, a little better that the noise is bouncing these curves back and forth, and the sine wave would be bouncing these curves back and forth, and when the Kramer's rate and the or 1 over the Kramer's rate equals the forcing function frequency, to within an order of magnitude, you're going to see stochastic resonance, right? Then one sample plot, schematic, right? But make sure that you've got the power supplies correct so that the hysteresis is correct, right? You got to change it to, and this again, this is just one sample, right, with a forcing function A and frequency, right? And then we have another plot. Again, this is just one sample, but make sure to use the VH that you had measured, right? And explain signal to noise ratio and full width half maximum here. Now, yeah, this is kind of hard to see, right? There's not much, it's just a solid wall of data, but that kind of means in this case it's working. If you saw something weird, right, you'd see that it wasn't reading it in. Now we have the full width half maximum results, and you can see I've got things by team member, and I have this thing called link to the data, right, which should take you to, this is a template drive where I've got sample data, right, and the Python plot used to generate it. What's missing right now is the signal to noise ratio data, fake data, and full signal to noise multiplot. So now's as good a time as any. So this plot, that's SNR. So this is just signal to noise ratio, right? I've got 3 files, 1, 2, and 3, and that would be group member 1, 2, and 3, right? And you would just, you have theta. Make sure, you can just download these files and modify them, but don't change these here because the Python needs those names to read it in. But enter in your hysteresis width, the signal to noise ratio you measured, your scale factor, and your theta, right? And so each team member would create and make sure to save it as a CSV, right? And so someone will have to kind of combine these files, right, into their own directory, right? And then here is data 1. We're going to read file 1, convert it to a data frame, and then extract theta, signal to noise ratio, and your hysteresis width. And for data 2 and file 3. Now, yeah, if you have a 4th team member, you're going to have to create another file name here, right? Maybe in this particular one, you'd want SNR4, right? You'd have to cut and paste this and change everything to 4. And then you'd have to add another line here, right? And so and we get that. And this is really just, one of these is real, right? And the rest I just kind of faked it so that you could see that it's different, all right? But you can see the hysteresis widths here, right? And if I want to add that image, it's probably better to upload it from the computer in that directory where everything is, right? Because it saves it in that directory. You can just click on the file you want, right? And so that's one. And then here's the signal to noise. And yeah, the link to that data, right? It should all be in whatever group you have. So if you're group 1, put all those files and your Python files here, right? And it should look like the group template. Again, what's missing is the signal to noise ratio Python plot, and then 3 signal to noise ratio plots, and I'll handle that. Well, I mean, the easiest way is just I can upload files. I'll just show you in case. So that's a file that's missing, and then my 3 data files. Okay, so if you just download the group template, right, and then open up the various files, you can enter in your measurements right there. All right, so back to, and then just have some discussion. Can you explain the LT spice versus your measured results, or explain the variance in results, right? And then some conclusions, and you can say, what did you learn? What would you change? It's up to you, okay? And you can feel free to get creative, put your pictures up front. But that's pretty much it, okay? And if I have all that data, right, we can verify everything, that it actually does what it says that it does. The paper that I followed was a good paper, but there were things that it was really hard for me to replicate exactly as in the paper. One, because a certain machine was no longer in, it's not made anymore, and you can't even find the lab manual on eBay. And so how they generated random numbers was a bit of a mystery. So I just had to kind of, at some point, recreate my own thing. And even knowing the op-amp part number that they used. Now they said, oh, the output is swinging between plus 15 and minus 15. Okay, and the resistances, you could see what the hysteresis width was. But getting that noise to look like the plot was problematic. At least now everything is laid out, and then anybody can download the files and repeat this work. And repeatability is important in science, although not always rewarded.